Okay, sweet. So today we're going to talk about homomorphisms and isomorphisms, right? And these are basically group functions. That's how you should think of a homomorphism. A homomorphism is like a group function. And of course, we've studied things in terms of their functions before. This is not in any way weird or mysterious. We do this all the time with linear algebra, right? With linear algebra, we always talk about linear transformations, right? And we're going to see that there are a lot of analogies between linear transformations and group homomorphisms. In fact, every linear transformation is a group homomorphism on the underlying additive structure. You remember one of the examples I gave as a group is if you take the vector space and you forget about scalar multiplication, the additive structure of a vector space is a group. And in the same sense then that a linear transformation has to preserve both addition and scalar multiplication, if we forget about scalar multiplication, linear transformations will be group homomorphisms. Okay, and that's exactly the reason why there will be so many analogies between group homomorphisms and linear transformations. Okay, but let's see why. And I really, really want to emphasize, ask lots of questions about this subject if it doesn't make sense to you. There are some people get this immediately. And some people need a little bit more time. There's a very deep subject, and it's going to take a while, I think, for you to get an intuition for what a group homomorphism is. So, ask lots of questions very, very early. Now, immediately, just straight out of the gates, let's define what a group homomorphism is. So let's say if I give you two groups, pen, what's going on here? I'm gonna have to buy a new pen here quick. Pretty sure I just changed the battery on this thing and it's still dying on me. All right, so we're talking about functions, so I need a domain and a codomain. That's what my two groups are. So G, what is going on? Why do I not have, okay. What is, uh-oh. I'm sorry, this is gonna get loud here. Okay, we're gonna try a new battery again. See if that fixes it. I blame the reading week. That's my opinion. The pen got lazy, forgot how to do stuff. Okay. Just survived the lecture, damn it. So far, so good. Let's not jinx it. Okay, so let's suppose that I've got two groups. I'm going to use G as the domain and H as the codomain. Then a function. We'll often use Greek letters, but if you want to call it F, that's totally fine. Then a function from G to H will be called a group homomorphism if it preserves the group structure. Okay, what does it mean to preserve the group structure? Well, we mean this. Okay, which again should sort of look like the sort of thing that we demand of a linear transformation, right? We often demand that t of x plus y is t of x plus t of y, right? Basically, the plus sign kind of comes out of the linear transformation. And we're saying that the exact same sort of thing is true for phi at the group level. Now, an important kind of note here to make immediately is that these are different group operators, right? So the group operation here is the G operation, right? And that makes sense because it's in the domain. So when I take G1 and G2, if I want to combine them, I have to use the group operation in G. But on the right-hand side, I'm looking at phi of G1 and phi of G2. Those are elements of H. So I have to, if I want to combine them, I have to use the H operation. Okay. Are all bijective functions from G to H homomorphisms? That's a great question. And not only that, we can even just ask, are all just functions, right? There isn't even a restriction that they have to be bijective, because you can see here in the definition, there is no statement about the function being bijective. Generally, no. And in fact, let's do an example, like right away. So here's an example. Okay, so let's take phi from Z2 to Z4. And let's map 0 to 0, and let's map 1 to 2. Okay, so I claim that this is a group homomorphism. In fact, I claim it's the only non-trivial group homomorphism, right? So let's check. First of all, let's check that this is a group homomorphism, and then let's convince ourselves that there are no other non-trivial group homomorphisms. And I said non-trivial here, and I haven't explained what that means, but let me do that in a second. So first, let's check that this actually does what we want it to do. And, you know, we could just check Z2 is small enough. We could just literally check every single element, right? We could do phi of 0 plus 0. That's equal to, yeah, 0, which is in fact phi of 0 plus phi of 0. The group is abelian. So if I want to check 0 plus 1, I only have to do it one time. So that's going to be phi of 1, which is equal to 2. And now is that equal to phi of 0 plus phi of 1? Yes, it is. Phi of 0, right? Because that's 0 plus phi of 1. And now the interesting one, phi of 1 plus 1, that's equal to phi of 0, which is equal to 0. And our question is that equal to phi of 1 plus phi of 1? Well, yes, it is. Right? So let's, again, you might have to take a second and think about what just happened here, but let's look at this. And is everyone convinced that I've actually checked this for every possible set of pairs in Z2 and showed that, yeah, it actually does split nicely, right? So is everyone fine with that? And then we'll answer Justin's question about are all functions group homomorphisms. Good. Okay, so what I want to do then, let's consider another one. And in fact, can anyone tell me how many maps are there from Z2 to Z4? Just how many set theoretic functions? Now, certainly we won't have bijections, right? So we don't want to worry about bijections. We notice that this map, while being injective, is not surjective, right? Nothing maps to 3, for example. So we don't necessarily want to worry about bijections, but we can just ask, are there any functions which are not group homomorphisms? So how many, can anyone tell me how many functions are there from Z2 to Z4? Anyone? Does anyone remember like their Math 202 knowledge? Like how do you count? Exactly, there are 16 of them, right? Basically, you have to decide what 0 maps to, right? And there are 4 options for that, 0, 1, 2, or 3. And then you have to decide what 1 maps to, and there are 4 options for that, 0, 1, 2, or 3. So that, by the basic counting principle, gives you 4 times 4 possible functions from Z2 to Z4. So there are 16 set theoretic functions from Z2 to Z4. I claim that the only 2 group homomorphisms are the following. Only 2 homomorphisms So there's the trivial homomorphism, which just sends everything to 0. Maybe let's call this the 0 map, right? Or maybe the identity. Let's call it the 0 map. Okay, so it maps everything to 0. And you should be able to convince yourself very quickly, yeah, that's a group homomorphism. Why? Well, because, yeah, everything just maps to 0. And if you take phi of x plus phi of y, if everything maps to 0, when you add those things up, you get 0. Okay, so convince yourself that's a group homomorphism. And then the function phi that we defined above. Okay, now I'm not going to give you a proof right now that these are the only two. So I'm going to ask you to take it on faith. I can do an example to show you what can go wrong. But these are, you're going to have to take it on faith right now that these are the only two group homomorphisms. So immediately what we see is that most of the functions from Z2 to Z4 are not group homomorphisms, right? So group homomorphisms, you've got kind of like the set of all functions. From G to H. And then the group homomorphisms are actually a very small subset of that. Okay, so generally, in fact, being a group homomorphism is such a powerful thing that almost no functions are group homomorphisms. It's in fact very, very rare. Okay, so does that kind of answer that question? Okay, cool. And in fact, excuse me, let's just choose another function. Right, let's just try something out and see what can go wrong. So if we take F mapping Z2 to Z4, and let's say we map 0 to the number 1, and let's say we mapped 1 to the number 1, right? So this is a nice function, relatively speaking. It maps everything to the number 1, to Z4. And we could ask, okay, is this a homomorphism? And the answer is immediately no. Well, let's try one. So F of 0, that's the same thing if F of 1 plus 1, right? Because we're in Z2 in the domain. So 0 is the same thing as 1 plus 1. And that has to be equal to 1. But if I take F of 1 plus F of 1, I get 1 plus 1 is equal to 2. And these are not equal in Z4, right? They're equal in Z2, but they're not equal in Z4. So immediately we can conclude, and in fact, this will break for pretty much any pair you do. If you do 0 plus 0, 0 plus 1, 1 plus 1, check those three pairings and see that, yeah, this doesn't work for any of them, right? F of 1 plus 1 is not equal to F of 1 plus F of 1. Right? And so because it fails that, it's not a group homomorphism. And again, just write down another one for fun. Just make one up and see if you can write it down and determine whether or not it is a group homomorphism. And you know, I've said that there are only these two, but yeah, right? You can actually give it a shot. Now, I guess something worth pointing out here is that there's always a homomorphism. From one group to another, there's always a homomorphism called the trivial homomorphism, which just maps everything to the identity. Right? So we should state that there's always a trivial homomorphism from G to H, which maps everything to the identity, right? Phi of G is the identity and H for all G and G, right? At the linear transformation level, again, if you're trying to keep this running analogy between group homomorphisms and linear transformations, this is like the zero map, right? There's always a trivial linear transformation between two vector spaces, the zero map, which sends just every vector to zero, right? And so in that context, this is the exact same thing, right? Give me any two groups. If I send everything to the identity element in the codomain, then that is sorry, let me turn off my phone here. Then that is a homomorphism, right? But it's a dumb homomorphism. That's called the trivial homomorphism. Okay. Now, can anyone see, like, immediately, there are a couple of very low level propositions that we can prove about homomorphisms. Again, I said we want a homomorphism to somehow preserve the group structure. Well, there's another part of what's the other critical part of a group? So we have an operation, the ability to multiply two things, but there's another critical part of a group. Something that really defines what it means to be a group. All right, because we have three axioms. Let's not worry about associativity. Associativity is going to be done for free. What are the other key parts of the group structure? Does anyone know? Transitivity, well, it depends on what you mean by transitivity, right? So usually we talk about transitivity in the context of a relation, right? If A is similar to B and B is similar to C, then A is similar to C. So that's usually what we mean by transitivity. But when I say, what does it mean to be a group? What are the defining properties that a group has? Sure, okay, identities and inverses, right? Exactly, right? Every group has an identity and every element in a group has inverses. So if a group homomorphism is supposed to, in some sense, preserve the structure of the group, then the hope is that it should do something special with the identity and it should do something special with inverses. And if you had to try and think about it in your brain, what should happen as I'm writing down this proposition? Okay, first thing, the identity must map to the identity. Right? And again, that's not crazy because again, we said one, a group homomorphism should preserve the structure. And if the identity is part of the structure of a group, then the identity should map to the identity. And again, we've seen this in the context of linear transformations. We know that the zero vector always maps to the zero vector, right? For a linear transformation, the same sort of thing is true. Now, this would be nice. It turns out it's not too hard to prove this, but yeah, it also preserves inverses. So the image of the inverse is the inverse of the image. In some sense, we might say that the homomorphism commutes with taking inverses. That's a reasonable thing to say. I guess I should say for all n and z, and for all g and g. Okay, and any power of g is also, right, or any integer power. Since, phi just kind of, what do I want to say here, distributes over the product, certainly exponents are going to be preserved as well, right? And so I'm going to prove all of these because they're very straightforward. And then finally, now this one we have to be a little bit careful about. The order of the image of an element does not have to be equal to the original element, but it does have to divide it. Okay, so if I take the image of an element and I want to figure out its order, then generally it must divide the order. It could be equal, but it for sure has to divide. And we'll figure out exactly, I will give you the exact criteria, which will tell you when these two things are equal in a second, okay? So let's start out by proving these. In fact, I think most of these are exercises in the book, and hopefully you've given them a shot. They're not too bad. They're very similar to these kind of like things we would have done in 102 when we were talking about fields, and you're kind of like proving, and it's just symbol pushing. It's just moving algebra around. So what I'm going to say is the following. So for number one, I'm trying to show that I map to the identity. So we know that this is true, right? The identity acting on itself just gives the identity. Now, because this is a group homomorphism, though, I can split that phi acting on the identity times the identity using the group homomorphism property. And you'll notice that I am being a little bit lazy here, and I'm not tracking, whether the operation is the G operation or whether it's the operation in the codomain. It's implied, right? Like it's the only operation that it could be in each of these cases. So we get that this is true. So if we multiply by whatever the inverse of phi of the identity is, right? We know that in groups, multiplication is left cancellative. It's actually right cancellative as well. This implies for us that the image of the identity is the identity. Right? So again, we can either say multiplication is cancellative in the group, or just multiply both sides of this equation by phi e.g. inverse, right? And that would give us that the identity map, or the identity element maps to the identity element. And so immediately we're seeing that, like, this is not, shouldn't it be E sub, oh yeah, you're right, it should be E sub H, thank you. So immediately we're seeing that, group homomorphisms have a lot of structure to them, right? The fact that all these things are true about group homomorphisms are not true of general functions. And so that's why there's so few of them, because they add so much, they have so much structure. Okay. For the second one, the fact that, inverses are preserved, pretty quick one. So the identity in H is phi times the identity in G. We just proved that in part one. Now let me write the identity as G times G inverse. Use the group homomorphism property. And so if I multiply both sides of this equation by phi, or like on the left, by phi G inverse, then I get what I want. Right? Three technically should be done by induction. I'm hoping that it's just clear. Is people okay if I skip it? Right? Like phi of G cubed is phi of G cubed is going to be phi of G times phi of G times phi of G, which is phi of G all cubed, right? And that's true for any n. Again, you would normally do it by induction, but like I think that it's clear enough. And then 4. So again, here's where things go a little bit wonky, and we're like, okay, maybe we need to refine our intuition for a group homomorphism just a little bit. So we want to show that the order of phi of G divides the order of G. Well, note that if I take phi of G and I raise it to the power of the order of G, well, I can put the order of G inside, right? Because it's an integer. And by part 3, you can take the integer exponent in and out of the homomorphism. Well, G due its order is obviously the identity. That's the definition of the order. So that tells us that phi of g to the power of the order of g is the identity. Now that doesn't tell us that the order of g is the order of phi of g, but we do know that it must be the case that the order of phi of g divides g, or actually, did I do this one backwards? Let me just think here. What am I trying to prove? The order of phi of g divides the order of g. Right, yeah, and that is what I want. Right? Namely that the order of g must be some multiple of the order of phi of g. If the order of phi of g is 7 and I raise it to the 21st power, yeah, that's going to work, right? It's still going to give me the identity. Okay, any questions about that? Because I want to give you lots more examples. I actually hadn't originally intended to go into this proposition so early, but it is nice because, oh, I just threw my pen. Because once you have this set of things, you can immediately do so much more. Like it opens the door to a ton of examples, a ton of counter examples, a ton of like non-examples show that isomorphisms, or sorry, show that there aren't any homomorphisms between these things, et cetera, et cetera, et cetera. Okay. Everyone's good? That makes sense? Okay, cool, cool, cool. Let's see. I guess I should give you a couple more abelian examples, and then I'll try and give you some non-abelian ones. Oh, you know what? Oh, that's a great one. Oh, let me throw that in. I'll throw it in a second. Let me give you some abelian ones first. Okay, so this one's really important. So let's suppose m and n are integers and m divides n. We're going to have to do a little bit of tracking in our brain to make sure that we remember which one of these is bigger. But my claim is that I can define a map pi n comma m from zn to zm. And all I'm going to do is map x to itself, but I'm going to change the modulo. Okay, so I'm going to change the modulo. This map is a group homomorphism. Okay, and we're going to check it, but let's choose an m and n to be concrete. All right, so for example, if we take Z12 to like Z4 or something, and what we're just going to do is we're going to take each element, and instead of computing it mod 12, we're going to compute it mod 4, right? So for example, here 0 is going to map to 0, 1 maps to 1, 2 maps to 2, 3 maps to 3. Nothing crazy. But now we're going to kind of repeat the cycle, right? We're going to take 4 to 0, 5 to 1, 6 is going to map to 2, right? Do you see what I'm doing here? Like 6 in Z12, I'm now going to reduce it modulo 4, so 6 will become 2. Right, like that. Okay, so I claim like that's what this thing is saying. Because 4 divides 12, there is an obvious map from Z12 to Z4, which is we just take the new modulo, right? And that is a group homomorphism. Okay, so I'm going to leave this one as an exercise for you to check, but the fact that this is a group homomorphism is immediate, right? But there is something you have to check. So that this is a homomorphism. Homomorphism is immediate since pi nm of x mod n times y mod n, right? Just the way we define, or I guess we're doing addition. So I should. That's defined to be x plus y, which then becomes x plus y mod m, which is x mod m plus y mod m. Like so, okay? But what do I actually have to check in order for this for me to be certain that this actually makes sense? There is something I have to check. So if this question came up on a test and we said, prove that this is a group homomorphism, and you write out this line, boom, that's half the marks. Where are the other half the marks? What's the other thing that you have to do? And this might be the first time in your career that you've ever had to do this. Anyone? I mean, I'm kind of like, the fact that I'm suggesting that it's the first time in your career that you have to do it obviously suggests that you probably not certain what to do, right? You have to check that this function is what? Zero plus zero, zero. Okay. So we know that that's true, right? On both sides of the equation. We know that 0 plus 0 is 0. And on the right-hand side in Z4, we know that 0 plus 0 is 0. Let me ask you this, though. So let's actually use the example above. Let's not use generic M and N. Let's use 12 and 4, right? So the map above, which maps Z12 to Z4. So I know that, say, 6 maps to 2. But what if the number that I plugged in was 30? What does 30 map to? So under the phi above, what does 30 map to? Phi of 30 is, what is 30 mod 4? This isn't a trick question. 2, thank you, Dylan, for your bravery. Now, phi of 30 is equal to 6. And phi of 6 is also equal to 2. But I've changed the mod, right? I'm changing what I'm modding by. How can I be certain that if I give you two numbers that are equivalent on the left, that they actually map to the same thing? What does it mean for me to say that I need to check that this function maps two equal inputs to the same output? What am I checking when I do that? We talked about it. I think it was the very first, like it was in the review portion of the course, right? It was like one of the first things that we talked about. What does it mean? What is this statement? Nobody? No. Injectivity is the other direction. Injectivity is if phi x equals phi of y, then x equals y, right? We're saying that it's not surjectivity, right? So injectivity says that the only way two outputs were equal is if they came from the same input. But what I'm saying now is that if I give you the same inputs, you get the same outputs. Yeah, exactly. Well defined. okay? Because this is a function on equivalence classes, right? And so because it's a function on equivalence classes, we have to check that the function is well defined. Let's see what could go wrong. What if I tried to define this? To Z5, and we did it exactly the same way. Okay. Well, in this case, we would get that phi of 5 is equal to 0, right? And phi of 12 is equal to 2. Do you all agree? Because I'm just going to take it at whatever number that you've given me, and I'm going to reduce it mod 5. Right? So 5 of the image of phi is 0, and the image of 12 is 2. But the problem is that 5 and 12 are the same number in Z7, right? I gave two numbers that are equal, but when I plug them into my function, I got two different numbers out. That tells me that my function is not well defined. In particular, it's not actually a function, right? So when I say up here that this map Zn to Zm, you'll notice that I have this condition here that m must divide n. The reason that condition is there is to guarantee that this is actually a function, that this function is well defined, okay? And you have to check it, all right? So I'm going to leave that as an exercise. It's 2 lines, and it involves some modular arithmetic. But I expect this not to be easy for you because you're going to have to, you're trying to, I think this is probably the first time in your life that you've ever had to think about what it means for a function to be well defined. This is a phenomenal exercise because it will tell you, it's, I think, your first exercise in actually showing that something is well defined. Okay. And I think it, like I said, this proof isn't hard, but it might take you some time to think about it just because you've never done it before. Okay, so it's a great exercise, and I strongly recommend that you give it a try, okay? See if you can wrap your head around what well-definedness means and then prove that this function is well-defined. Okay? Are there any questions about that? Does that make sense? Okay, here's an exercise. How many group homomorphisms? How many group homomorphisms are there from Z4 to Z7? 100% a fair question. Find all of them. And again, set theoretically, right? We know that there are 7 to the power of 4 functions that do this, right? That's a crazy number. That's something on the order of 2,500, right? It's a little bit less than that, but it's about 2,500 functions from Z4 to Z7. Now I'm asking you, how many of them are group homomorphisms? How many of these about 2,500 functions are group homomorphisms? Does anyone have a guess? Because obviously, if I ask you this question, and this is 100% a valid term-test question, at least, thank you, Karina, that's very much the political answer, right? There's at least one. But absolutely, you're right. There is at least one, right? Because this is the trivial homomorphism. But this is a great question. Are there any others? Is there another group homomorphism? Okay, I'm going to give you a big hint. Just remember the question. Scroll up, scroll up, scroll up. Look at property 4 there. So property 4 says that the image, the order of phi g must always divide the order of g, right? This is our critical thing. This number 4 here, you might say like, okay, fine, whatever, who cares? But this property of homomorphisms is really useful for classifying all the possible homomorphisms from one group to another. It's very, very important for that, because all you have to do is say, look, I can immediately throw out any function which doesn't satisfy this property, right? So, I mean, first of all, immediately, you can obviously throw out any function which doesn't map the identity element to the identity element, right? That really narrows down the number of functions that you have. But as well, anything which doesn't, in some sense, preserve, I don't want to say preserve the order, but preserve this multiplicity of the order. Anything which doesn't do that can be thrown out as well, right? So the things of Z7, what are the possible orders of elements in Z7? Not a trick question. What are the possible orders of elements? Remember, it's cyclic and abelian, so we know exactly what the orders of elements in here are. What are they? Like, what's the order of 2, the order of 3, the order of 4? Does anyone know? No? Ignore the background, the man behind the screen. So everything, so certainly there is an element of order 1, right? That's the identity element. Every other element has order 7. Does everyone agree? So the idea here, this isn't how we're going to prove it, but this is the key to the idea. Everything in Z7 has either order 1 if it's the identity, or order 7 if it's anything else. So everything in Z7 has order 1, the identity, or 7. Do you agree? Right? Because Z7 is cyclic, and every element of Z7 that's not 0 generates Z7 because it has order which is co-prime to 7. Right? So now what are the possible orders of elements in Z4? Anyone remember? So 1, obviously the identity element has order 1. Nobody remembers, eh? Okay. Very close. 1, 2, but not 3. What's the other order? For example, what is, yeah, exactly, it's 4. Okay, remember when we were talking earlier, previously when we were talking about cyclic groups, we learned that the order of the elements of a cyclic group must divide the order of the group, right? So the only possible orders of elements of Z4 are the divisors of 4. So that gives us 1, 2, and 4. That's the same thing I got for Z7, right? The only possible orders for elements in Z7 are the divisors of 7. So it's 1 or 7, right? And so now so now the question is, could there possibly be a non-trivial group homomorphism from Z4 to Z7? Well, no, because if there is one, then we have to have that the order of the image of a non-trivial element must divide the order of the original element. Exactly. 1, 2, and 4 don't divide 7. And conversely, 1 and 7, like 7 doesn't divide 2 or 4, right? So there can't be any group homomorphisms. Now, the way you would actually prove this is you would do it by contradiction, right? You'd say, for the sake of contradiction, suppose there is one. So for the sake of contradiction, suppose there's a non-trivial right? Because if it's trivial, it does exist, right? We know the trivial homomorphism is certainly one. So suppose there's a non-trivial homomorphism. Let's call it phi from Z4 to Z7. So I'm going to say fix some element. And I don't want this element to map to the identity, right? Because I don't want its order to be 1. Right? So then the order of phi n must divide n, but the order of phi n must be 7 because it's not the identity. So 7 does not divide 1, 2, or 4. So we've got our contradiction. Does that make sense? Right? And actually, we've kind of been sweeping something out of the rug, which is we've been saying, and sorry, we're doing a fire alarm test. But we've been saying that, for cyclic groups, we know that the order of an element must always divide the order of the group. But this is actually universally true, okay? You always, and we're going to learn it in a couple of weeks here, but the order of an element must always divide the order of a group. And if you want, you can kind of cheat and put that, bit of knowledge in the back of your brain and use that to help you in order to make these sorts of arguments, okay? The order of an element must always divide the order of a group, okay? Well, okay, right, Justin, good question. So, but can't we find a non-trivial mapping such that nothing maps to something of order 7? We can, but we can't because the only thing that does that is the trivial map. Because the order of every element of Z7 that isn't the identity is 7, right? The order of 2 is 7, the order of 1 is 7, the order of 2 is 7, the order of 3 is 7. Everything has order 7 except the identity. So if you want to map everything to something which doesn't have order 7, it has to be the trivial map, right? Everything had to map to the identity element. So that's why this works, right? Is specifically because everything has order 7. If this was a map from Z4 to Z8, there absolutely is a homomorphism from Z4 to Z8. Right? Because we wouldn't be able to make this argument anymore because suddenly in Z8, there are elements of order 1, 2, and 4, and 8, right? So we wouldn't be able to make this argument. And in fact, there is a homomorphism. Right? So if you take every element in Z4 and you double it, that is a homomorphism. And you can check in that case, and that actually does do the order thing that we want. So here it was critical that it was actually a prime number, right? And you can probably guess that what do I want to say here? If you're trying to map into ZP for some prime P, like there aren't too many things which are going to do that, right? You can certainly map ZP to ZP. That's not a problem. But generally, there are not a lot of non-trivial homomorphisms from a group into ZP, right? Because again, of this, the fact that you have to divide the orders. Okay. I mean, you could, for example, map Z14 to Z7. That's okay. But, right, keep that in mind. Okay, let me, I'm going a little over here. Normally, this is when we would take our break. Man, I hate these stupid Monday fire drill things. But I want to leave you with the following sort of 2 questions that I want you to think about. So let's see. So above, we said that we can always map downwards, right? That's what this example says. It says, I can always map from a big number to a smaller number, which divides it, like Z12 to Z4. It turns out if n divides m, right, which is the opposite of this case, if n divides m, there is also a group homomorphism in the other direction. All right, so exercise, like in this case, Z4 to Z8. So if n divides m, so there's a group homomorphism from Zn, non-trivial. From Zn to Zm. Okay. The other thing I want you to do, actually, and somebody remind me if we've defined this yet. If we define GLNR in this class, Ali might have put it in brackets, like GL bracket N comma R. But do you remember what this is? No? Okay, so this is a set of all invertible n by n matrices. Such that A is invertible, right? So does that make sense? What GLNR is? Take all the n by n matrices which are invertible. You know that, right? You know what all those words mean because we've all done linear algebra. And we know that that's a group under multiplication, right? And because the product of two invertible matrices is invertible, the identity matrix is invertible, this is a group. And I'm pretty sure it's mentioned in the notes. This is a group. R star over on the right-hand side is the non-zero elements of the real numbers under multiplication. What I want you to tell me is there a group? Can you think of a group homomorphism from GLNR to the group of units of R, right? So the non-zero elements of R under multiplication. Okay, so that's sort of like what I want you to think about. There are these two exercises here. Neither of them are particularly difficult, but see if you can solve them. Now, at this point, let's take a 10-minute break, and then we'll come back and I'll give you little hints for these if you're interested, but otherwise we'll kind of move on. We'll start to talk about isomorphisms, which are, you know, we've heard that word before in the context of linear algebra. We've heard the word isomorphism before, and it's going to be very similar for groups. Okay, so I have 209 by my watch. So I'm going to say 2:19 by my watch. Otherwise, just set a timer for 10 minutes and we'll come back and we'll pick up then. And again, don't hesitate to throw any questions you have in the chat. I'll be around and I'll answer them as they come up. Okay, so 10 minutes and I'll see you in a little bit. Resume. All right, did anyone make any progress on these? Even if you just write them down. Could anyone think of a homomorphism from GLNR to the group of units of R? Nothing. That's too bad. Such a fun little question. Okay, so I'm going to let you work out the details, but I'll tell you what the answer is for the second exercise. The determinant map is actually a group homomorphism, right? It certainly maps the identity to 1, right? The identity map goes to the number 1, which is the identity of the group of the multiplicative group of real numbers. And the determinant map is itself multiplicative, right? The determinant of AB is the determinant of A times the determinant of B. We know that, boom, it's a group homomorphism. So, you know, that's kind of cool. I think that's a neat little thing. Let's see. Oh, you know what we should do? We should talk about kernels and images. Now, you've heard these words used in linear algebra as well, right? And again, it plays a lot of similar analogies in group theory. So let's I mean, their definitions are actually the exact same. And a lot of the properties are the same as well. So phi mapping G to H is a homomorphism. Then the kernel is a set of all things which map to the identity. And so it's the collection of all G's such that phi of G is the identity. Again, that's pretty much the same definition as it is in linear algebra. In linear algebra, you say the kernel is the collection of all elements which map to 0. But remember, 0 is the identity in a vector space, right? So we're saying, what are all the things which map to the identity? Exact same sort of thing. The image, well, nothing crazy here. There's a set theoretic definition of an image, and that agrees with the group theoretic one. So the image of phi is the collection of all elements that phi hits as a function. All right, so it's a collection of all elements such that there's something in G which maps to it, or we could write this, I kind of like this other way a little bit better, even though it's not as proper. It's the collection of all phi G's, such that G is in G. Right? Those are the same thing, but it's just saying, hey, look at what, it's basically, it's the range, right? In this case, it's the range of the function is the image of phi. It turns out kernel of phi is a subgroup of the domain, and the image of phi is a subgroup of the codomain. Both of those proofs are very easy, and I'm going to give you a chance. You should do them. 100% you should do them. I think they're also left as an exercise in the textbook. I don't remember, but no matter what, 100% you need to do these. Okay, they are not difficult, but if you're struggling at all, throw it up on Piazza. I'm happy to help. So show that the kernel of phi is a subgroup of G, and the image of phi is a subgroup of H. Okay. Now, we know that being surjective has something to do with the image of phi, right? Namely, if the image of phi is everything, is all of H, then we know that our function is surjective. And it would be nice, because we know that there's this injective-surjective duality, it would be nice if we could say something about a function being injective and its kernel, right? If there's some way that we can relate this. And again, if you think back to linear algebra, we do have that theorem there as well. So in linear algebra, we have the theorem that the kernel, that a linear transformation is injective if and only if its kernel is trivial. And that exact statement is also true for groups. So a group homomorphism will be injective if and only if its kernel is trivial. So what do I want to call this? I think this is a theorem. This is a pretty significant result. Is a homomorphism, then phi is injective if and only if the kernel of phi is just the identity element. Okay, so it's trivial. The proof is exactly the same as the one that you do in linear algebra. It's word for word identical. The only change is that instead of a plus, we're going to use the group operation, but otherwise it is the same. Okay, and I think it's worth kind of going through it to see why it's true. So let's suppose that phi is injective. in which case I want to show that the kernel is trivial. So let's choose an element of the kernel. What I want to do is show that G is the identity. And what that says is that no matter what element of the kernel I chose, it ended up being the identity. So the kernel is trivial, right? It is just the identity element. Well, what does it mean to be in the kernel? Well, phi of G has to be equal to the identity, but we know that there's something else which maps to the identity as well. The identity also maps to the identity. And now we're done because we know that phi is injective. So if both G and E map to the identity, then G had to be equal to E. And since phi is injective, G is the identity. Okay, the other direction, very similar. So suppose the kernel is trivial. And that phi of G1 equals phi of G2. So we want to show that G1 is equal to G2, right? That's the requirement for phi to be injective. Well, all I'm going to do is basically use the group homomorphism properties to bring everything onto the left-hand side. So you get phi of G1, phi of G2 inverse is the identity. So phi of G1, G2 inverse is equal to the identity. So by definition, what have I shown? Well, I've shown that G1, G2 inverse maps to the identity, so it's in the kernel, but the kernel is trivial. So G1, G2 inverse has to be the identity. i.e. G1 is equal to G2, right? And that's it. So we can determine injectivity just by examining the kernel, simply by looking at what elements map to the identity. That's hugely powerful. And really, it all comes down basically to this fact, right? The fact that if you have phi of G1 is equal to phi of G2, then you can basically manipulate this into this statement. And that's, right, the thing to remember is that if you start with the condition, the injectivity condition, it's easy to relate it back to a kernel condition. And those two things correspond precisely, right? So they work out perfectly. That's why we managed to get this theorem. And of course, here it was important for there to actually be a group homomorphism, right? Here we use the group homomorphism property. So that's why this doesn't work in general, right? We need this condition to be true in order to be able to make such a strong statement, okay? Now, injectivity is huge because the moment you get injectivity of your homomorphism, you get a ton of stuff, okay? I'm going to leave this as a quick little exercise, but again, very good exercise to do, and both of these are pretty easy. So let's suppose that phi from G to H is an injective homomorphism. So one, show that if K is a subgroup of G, then K is isomorphic to its image. Oh, damn, I haven't talked about what isomorphisms mean yet, so I can't actually talk about this theorem. Okay, so then we're going to change this, show that the order of phi of G, and now there's only one, so show that the order of phi of G is equal to the order of G for all G in G. Okay, so we know that the order of phi of G has to divide G, the order of G, and I said I would tell you exactly the condition for that to be equality. The condition is injectivity. If your function, if your group homomorphism is injective, then you can be guaranteed that the order of phi is in fact the order of G. Okay? So you need injectivity in order for this to be true. In fact, I'm not certain if this is an if and only if. This just occurred to me. I was just thinking to myself, is this an if and only if? And honestly, I don't know. So I don't know if the converse direction is true. And I'd have to think about that a little bit. Okay. But it'd be cool if one of you could answer that before me. I think that'd be really, really awesome. Right. So is this an if and only if? Either prove it or provide a counterexample. I think that would be a really cool thing to do. All right, so kernels and images, super important. We're going to use them a ton. Kernels more than images, right? Kernels are super, super important. And you know that, I think, again, even from linear algebra, right? So make sure that you're very comfortable with the notion of a kernel because it's going to pop up everywhere, right? Super important. Okay, let me dive into isomorphisms because I just tried to say the words isomorphic and couldn't because I hadn't defined it yet. And yeah, what do I want to say here? I mean, one of the problems, maybe I should just define it first and then tell you why I hate this definition. Okay, I'm going to define it and I'll tell you why I hate this definition. So definition. So a homomorphism from G to H is an isomorphism if phi is bijective. Okay, so a bijective homomorphism is called an isomorphism. And that shouldn't be surprising. Again, linear transformations, exact same thing, right? A bijective linear transformation, we said, was a linear isomorphism, right? So we have exactly the same sort of thing being true for groups as well. Now, what I hate about this definition is that it doesn't tell you what's going on. What I basically want to be able to say is that basically what I want to be able to do is say, look, these two groups are actually exactly the same thing. Okay, they might be written in a slightly different way, but they are secretly exactly the same thing. Okay, in this case, we say G is isomorphic to H, and the way that we write that, same way as in linear algebra. We write G as isomorphic to H like that. Okay, so two groups are isomorphic precisely when there's an isomorphism between them. The idea, isomorphic groups are the same group. Isomorphic groups are the same. Right? This is the idea. They might be written a little bit different, but they are in fact exactly the same group. Okay? That's the idea. So, crud, which one was it? Yeah, let me think here. There's a bunch of like dumb isomorphisms. I guess, okay, let me just give you like kind of a dumb one first, and then I'll give you kind of a more interesting one. So, oh, actually, okay, let me say the following first. This is a bad definition of an isomorphism. Okay, I hate this definition of an isomorphism. It's universally what everybody uses, but I think it's stupid. And if you've ever, I think one of you, right, at least one of you here did have me in 224 as well. And I said the exact same thing about the definition of a linear isomorphism then, right? I said, this is a stupid definition and let me show you why. So it's the exact same thing is true here. Why? The proper definition of an isomorphism is the following. It should be that phi from G to H is an isomorphism if there exists a function, or if there exists a homomorphism. Such that phi compose psi is the identity on H, and psi compose phi is the identity on G, right? i.e., that phi is bijective, but importantly, that its inverse is also a homomorphism. Okay, so the proper definition of an isomorphism is a bijective homomorphism whose inverse is also a homomorphism. Must also be a homomorphism. Okay, and you might say, well, like, who cares, right? Why are you saying this? Well, okay, a couple of things. Remember, the idea of a homomorphism is that it somehow preserves the structure of its domain and kind of embeds that group into the codomain. So if you have a map phi, which can embed the information about G into H, and then you have another homomorphism from H into G, which similarly embeds the information about H into G, well, the only way that both of those things can be true is if G and H are in fact the same group, right? That's sort of the idea there. So that's kind of a first level understanding of why we would demand that there's an isomorphism, or rather a bijective homomorphism going this way and a bijective homomorphism going the other direction. Now, it just so happens that these are equivalent for groups, okay? So for groups, if I give you a bijective homomorphism, its set theoretic inverse also happens to be a homomorphism. Okay, does everyone understand what I'm saying? So look at our first definition of an isomorphism. We're told that an isomorphism is a bijective homomorphism, right? Since it's bijective, we know that it has an inverse, but we don't know that the inverse is itself a homomorphism, right? Because we said, in fact, most functions, even if the function exists, there's no guarantee that it's a homomorphism, right? So if I give you a bijective homomorphism, its set theoretic inverse exists, but we can't guarantee that it is actually a homomorphism. But it turns out you can prove it. You can prove that it actually is a homomorphism, right? And the exact same thing is true for vector spaces. If I give you a bijective linear transformation, its inverse is also a linear transformation, right? You know its inverse exists set theoretically, but you don't know that it's linear, but it turns out you can prove it. So the second definition is the correct definition, okay? If I give you a homomorphism, it is an isomorphism if and only if its inverse is a homomorphism. And the reason why this is important is because when you start to study more or different spaces, especially topological spaces. So some of you have probably heard about topology. Is anyone like doing any topology right now? Is anyone like taking the topology class? It'd be very interesting if you have. And so you can just let me know in the chat. Did a bit in 236, took one. Okay, so yeah, for sure. What you are going to learn when you take topology is there's a notion of a topological homomorphism. And in fact, most of you already know what that word is. You would have learned it in first year calculus. The word is continuous. So when you learn topology, there's a structure of a topological space, and a homomorphism should be something which preserves that structure. And what you're going to learn is that the thing that preserves the structure is called a continuous function. So continuous functions preserve topological structure. But bijective continuous maps do not have to have continuous inverses, right? And this is kind of a weird thing. Like you might struggle a bit to think about this, but you can have a bijective continuous map whose inverse is not continuous, which means that when we define the correct notion of isomorphism in topological spaces, we really have to say it is a map which is bijective and continuous, and its inverse is also bijective and continuous, right? We have to explicitly state that because we can't prove that the inverse is continuous just by assuming that the original function is continuous. Here, if you assume that the function is a bijective homomorphism, you get the inverse as a homomorphism for free. You can prove it. But bijective and continuous does not imply that the inverse is continuous. So as you start to study more and more algebra and more spaces, the notion of an isomorphism is universal. It is a structure-preserving map whose inverse is also structure-preserving, period. That's the definition of an isomorphism. In linear algebra and in group theory and in ring theory, we cheat and we say, if you're bijective, that's enough. Turns out, if you're bijective, you don't have to check if the inverse is a homomorphism. You get it for free, right? But it disguises what's actually happening. And so that drives me insane, okay? Now, I do believe this one is proved in the notes, in at least one direction, but both directions are similar. And because unfortunately I went on a little bit of a rant, I'm not certain I'm going to get time to do this. No, I could probably do one direction. So let me show you. So one direction, and the inverse direction is the exact same. So I claim if phi from G to H is a bijective homomorphism, i.e. an isomorphism, then its set theoretic inverse. Okay, this isn't a group theoretic inverse. This is its set theoretic inverse. This is just a function. So the result that I'm proving is that this is also a homomorphism. Okay, and you can see this is actually if and only if, right? Because if the inverse is a homomorphism, then so is phi, just by flipping the relationship of phi and phi inverse, right? They're just inverses of one another. Who cares what the original function is and which one is the inverse? You just flip the relationship between them, right? So once we prove this, we've gotten the whole thing. So let's say let H1 and H2 be elements of H. Now, since phi is a bijective homomorphism, it's surjective, so we can find elements which map to H1 and H2. And choose G1 and G2 in G such that phi G1 equals H1, phi of G2 equals H2. And then note that, well, because phi is a homomorphism, phi of G1, G2 is H1, H2, right? Okay, now it's easy to lose the forest of the trees. What are we actually trying to show? Well, we're trying to show that phi inverse, we're trying to show that phi inverse is a homomorphism. Right? Namely, I'm trying to show that phi inverse of H1, H2 is phi inverse H1, phi inverse H2. And well, that's equal to G1, G2 because of this equation. And yeah, that's equal to phi inverse H1, phi inverse H2 as I wanted, right? And so I'm done. And so again, I was able to do that. And again, if you go back and you look at your linear algebra proof of this, you'll find the linear algebra proof is the exact same. And again, unless you've done topology, you haven't seen this notion of an isomorphism break down, that it's not enough to be bijective and structure preserving to guarantee that the inverse is also structure preserving, but that'll happen if you go on, you study a little bit more math like topology. Topology is probably the most famous case where this occurs because it's such an important, like topology, like algebra, is so critical, everybody uses it. And so understanding what an isomorphism of topological spaces is very important. And this is famously a case where this does break down. Okay. Okay. Now, the notes at this point go into a lot of detail and say things like, oh, if phi is an isomorphism, then it perfectly preserves the order of groups, and G is G is abelian if and only if H is abelian, and G is cyclic if and only if H is cyclic, right? And I'm saying, like, there is a sense in which, yes, you do have to prove these things, but alternatively, they're obvious. Because again, what did I say? I said the idea, look at the green comment at the top of the screen. The idea, isomorphic groups are the same group, right? So yeah, if one group is abelian, obviously the other group is abelian. They're the same group. They look different, but they're actually the same, right? If one of those groups is cyclic, then yeah, the other group is also cyclic. And that's the idea of an isomorphism that you really need to like grind into your brain. Isomorphic groups are the same group. They are exactly the same group. They might look different, but they are the same. So here's kind of a stupid example, or maybe it's not stupid. Okay, so remember we talked about U5, which is the group of units in Z5. And we said this is 1, 2, 3, 4, and this is under multiplication. And so we talked about this group much earlier in the year, week 1, week 2, whatever. And we said, for example, well, notice, for example, that 2 squared is equal to 4, 2 cubed is equal to 8, and 2 to the 4 is 1, and then 2 to the 5 is, why am I screwed up? Oh, sorry, not 8. 8, it's obviously 3, right? And then 2 to the 4 is 16, which is 1. And then 2 to the 5 is 32, which is 2. Wait, why am I bugged by this? Oh, no, yeah, because I'm back at the identity already, right? 2 to the 1 equals 2, like that. Okay. So the order of 2 is 4. Right? Everyone agrees? Right? 4 was the first power of 2 for which I got back the identity. And in particular, this tells us that U4 is, or U5 is cyclic. I claim that in fact, U5 is isomorphic to Z4. Okay, and it turns out all cyclic groups, if I give you a cyclic group of order n, it's isomorphic to Zn, period. That's always true, right? So U5 is isomorphic to Z4. I'm going to let you try and figure out what the isomorphism is, but it's not too hard. Okay, here's another one. S3 is isomorphic to D6. Right? So remember, S3 is the symmetric group on 3 letters, and D6 is the collection of symmetries of the triangle, right? And I claim that there's a sense in which this is obvious. In fact, this is the only time the symmetric and the dihedral groups will be isomorphic. Okay. After this, obviously, it's not true, just because they don't have the same order, right? S4 has 24 elements in it, but D8 only has 8 elements in it, right? And very quickly, you get that n factorial is bigger than 2 times n. So this is the only time where n factorial is equal to 2 times n, right? 3 factorial is equal to 2 times 3. So this is the only time this is true. Now, but I claim that there's a sense in which this is obvious. So first of all, we can just construct the isomorphism explicitly if that's something that you would like to do. Again, let's maybe draw the triangle. Let's call this 1, let's call this 2, let's call this 3. And hopefully immediately you're seeing like, oh, wait a second, you labeled the vertices 1, 2, and 3. That seems like it's going to be in some sense obvious how the permutation group shows up. Because if I apply a rotation, and this now becomes 3, 1, 2. Well, this looks like a permutation, right? It looks like 1, 2, 3, right? The vertex 1 became, or sorry, 1, 3, 2, I guess. I should have done my vertices clockwise instead of counterclockwise. But 1 went to where, did I screw this up? Oh no, it is 1, 2, 3. Sorry. Right? 1 went to where 2 was, 2 went to where 3 was, and 3 went to where 1 was. Right? So there's a very real sense in which that permutation is like this. Okay, what happens if I do a flip? Let's say I flip about this vertex here, right? So if I flip, then I get 1, 3, 2. Right? So that looks like phi of the flip should be, well, what happens? 1 stayed the same and 2 and 3 flipped. Right? And you can check now that you know that the dihedral group so this is the identity R squared F R F R squared F. What we're going to do is we're just going to say define phi to map these things to what you think they should map to and check that this does in fact give you an isomorphism. Maybe I should give this a power m. And check that, yeah, this actually works. This generates all of S3 for you. Okay. Alternatively, there's actually a much easier proof. Hopefully what you do is you believe that the dihedral group always embeds into the symmetric group. So maybe let me say a comment. Note that there is always an injective map phi from D to N to Sn, right? Because as I just said, every single possible symmetry of the regular n-gon is just a permutation of its vertices, right? And so this gives you a natural homomorphism from the dihedral group of the n-gon into the symmetric group. Now, most of the time, that's not an isomorphism because it doesn't have a chance of being surjective. In our case, though, you just see, listen, it's injective. Both of them have order 6. It has to be bijective, and you're done. When n equals 3, the order of D6 is equal to the order of S3. So phi is a bijection. Right? If I give you an injective map on something with 6 numbers into something with 6 numbers, it actually has to be a bijection, right? Hopefully we remember that from like 102, right? If I give you an injection from a set of 6 elements to a set of 6 elements, then it's actually a bijection. Same thing, if I give you a surjection from a set of set with 6 elements to a set of 6 elements, it's also a bijection, right? So we get that for free. So you can check it. You can construct the isomorphism from by hand, or you can do this sort of like nice, sort of tricky way of doing things in green, where you say, look, always the dihedral group embeds into the symmetric group, and they have the same number of elements, so boom, they have to be isomorphic in the case where n is equal to 3. Okay? Any questions? Okay, let me really quickly hit something. So the notes tell you, and if you don't remember this, you should go back and check the notes. The notes tell you that these two things are isomorphic. Right, so the notes tell you that the additive group of real numbers is isomorphic to the multiplicative group of real numbers if you take away 0. And the fact that the exponential map actually gives you the isomorphism is kind of interesting. Now, what if I take a subgroup? Is it still true? Okay, so this is a fun question. As far as I'm concerned, this would be a great exam question. What I want you to think about, though, in particular, is I'm just going to tell you what the answer is. The answer is no. And the way that you should prove this is by contradiction. Suppose that there is an isomorphism between these two groups, and basically somehow construct an irrational number. Show that if you had an isomorphism between these two groups, then you would be able to make an irrational number appear on one of these sides. Okay, in particular, a natural thing to do might be the square root of 2. Somehow the square root of 2 is going to show up. And we know the square root of 2 is irrational. So boom, that would give us our contradiction. Okay, so I want you to try that. And can anyone give me a one-line answer to this? So take the multiplicative real numbers and the multiplicative complex numbers. These are both groups. And in fact, there are bijections between them, right? The cardinality of R is the same thing as the cardinality of C. And so if I take away 1 point from either of them, it's not going to change the cardinality. But is there a group? And in fact, there's definitely homomorphisms. Okay, there are definitely homomorphisms from the multiplicative reals into the multiplicative complex numbers. Are there any isomorphisms? Can anyone give me a one-line answer to this question? Last thing that we do today. Complex, right? A plus IB. Under multiplication still. Anyone? Any ideas? Let me ask you the following. Are there any real numbers that have order 4? In fact, what are the only elements of, okay, yeah, what are the only elements of finite order in the multiplicative reals? Which elements have finite order? So 0 is not in there though. Remember, because I'm doing multiplication. So we don't want 0 because then 0 wouldn't have an inverse, right? So we've taken 0 out. 1 and -1, right? Exactly. Okay, so the things of finite order. Finite order. What are the finite order things on C? Well, actually, okay, so there's a lot of them. So maybe that's not fair of me to ask. But can someone tell me one that does, so the 1 and -1, for two groups to be isomorphic, they need to have the same cardinality. Oh, so Justin, R and C actually do have the same cardinality. So Dres, is that -I? Is that what you chose? I, okay. Yeah, so I has, yeah, plus and minus I are in here. Obviously, plus and minus 1 are also in here. And there's a lot more things. Now, importantly, what's the order of I? How many, what's the, yeah, exactly, it's 4, right? I to the power of 1 is I squared is -1, I cubed is -I to the power of 4 is 1, right? So there's an element in the multiplicative complex numbers that has 4. Look at the left-hand side. The only two things that have finite order are plus and minus 1, right? And the only, like 1 has order 1, -1 has order 2, nothing in there has order 4. The only, so can there be an isomorphism between these two groups? No, because isomorphisms have to preserve orders. If there's an isomorphism between these two groups, then there must be something in the multiplicative real numbers that has order 4. And there's nothing in there that has order 4, right? So there's no isomorphism. Does that make sense? Does everyone see like how I can kind of just one line that, and I can see that there are, you know, there's an element of order 4 on the right-hand side. There isn't one on the left. So they can't be the same group. They have to definitely be different, right? In fact, can anyone tell me what are the group of units, or what are the things of finite order here? Does anyone actually know? I'll let you think about that. I'll see if you guys can think of what those things might be. Okay. All right. Otherwise, though, I think we're good for the day. Hopefully that made a little bit of sense for you. And if not, again, these are my office hours, so I'm happy to hang around and answer any questions that you have. Otherwise, though, I think we can call it a day, and I will see the rest of you on Thursday. All right, so for those of you who are leaving, see you later. For those of you who are staying, don't hesitate to throw up any questions that you have.